Hi everybody. We're going to pick up where we left off on a discussion of the nature of light. So you just got done learning about the photoelectric effect, where essentially to explain how photons of light can knock electrons off of atoms, ionize them if you will, you have to treat the photons as particles with an energy of HF. If a photon of light comes in with an energy less than the ionization energy of an atom, then it ignores it. And if it comes with greater than that, then it'll knock it off. So that was Einstein's solution to a problem that he borrowed from Bohr. Or excuse me, not from Bohr, from Planck. So at this point, we're around 1910 or so when Millikan verified Einstein. And so we're puzzled. What exactly is light? We know previously from Maxwell, from Young's experiment, from polarization, it's definitely a wave. Now we have two phenomena that the only way we can explain it is by treating light as a particle that comes in bundles of energy. So if we jump a decade, the final nail in the coffin comes from a very interesting experiment carried out by a guy named Arthur Compton in 1923. And so I'm going to talk about this diagram right here. And it's a schematic, and it's a fairly straightforward one. At the time, or maybe a few decades earlier, a guy named Renton had discovered something called X-rays. They were called X-rays because we didn't know what they were. We weren't sure if they were a new particle like an electron or a proton, or if they were light. So what Compton did is he took X-rays, a source, he had a source, and he fired them at electrons, and he saw what happened. And if you look at the schematic here, we see that the electron scatters, and then we have a photon that also scatters. And if you look closely at this photon here versus the one that came in, you'll notice that its wavelength is slightly longer. So what are we to infer from this? Well, they certainly did not diffract around the electron as one might expect a wave to do. Instead, and this is what the most startling part is, the most important is, it collided with the electrons. All right, that's exactly what this is showing. Okay, more so than that, it transferred energy, as you might expect, but more strangely, momentum. Okay, and this implies, if you're going to transfer momentum to the electron, that the photon has momentum. Why is that odd? Because photons, whether you treat them as a particle or not, have no mass. And yet, we see exactly what we'd expect for any collision. And so this was really a significant finding. So to sum up, photons of light have momentum, even though they don't have mass, and upon colliding with electrons, energy and momentum are conserved. So even with this weird behavior of light, we see conservation momentum still holds. And that tells us that the momentum is really fundamental to nature. Okay, so there's an equation that goes with that. One is in the reference tables, the other one is not, but it's the one I'm going to give you that's not is pretty important. And that relates energy to momentum, okay, in a non-classical way. I'm not going to derive this equation. It might come up later. But an equation that we know is the energy of a particle, okay? And this is not a photon per se, is P times c. It's momentum times the speed of light. That comes out of Einstein's relativity equations. So we'll accept that for now. So if I'm applying energy to a photon now, so this could be a particle, this could be an electron. I could say the energy of an electron is equal to its momentum times the speed of light. But I could also do it for a photon. So if I apply Planck's law, I know the energy of a photon is, I'm going to do it down here, is hc over lambda, right? That's just the version of hf. If I set that equal to pc, then I can relate momentum to wavelength, right? I see that the c's cancel out, and I see that the momentum of a photon is Planck's constant divided by the wavelength of light. So we have a p lambda is an inverse, kind of like energy. Okay, so now we have light has momentum. And if I want to know the momentum of 200 nanometers, which is, let's see, that's an ultraviolet part of the spectrum. Okay, then this is a fairly simple. P is h over lambda. And once again, we got the 6.63 times 10 to the negative 34 units. divided by 200 times 10 to the negative 9th meters. Punch it out on your calculator, and we get something times 10 to the negative 27th, right? 3.3 times 10 to the negative 27th kilogram meters per second. Okay, the value of this is not so significant, except the fact that, A, it's a tiny value, as one would expect, and the fact that light has momentum at all is odd, but verified, okay? And that's the key thing what Compton did. He verified what Einstein had predicted about any particle, even if it doesn't have mass. So now we're going to bring it all together. This is a conclusion from all three phenomena we've been talking about on this note sheet. Planck's law to explain black body radiation, photoelectric effect, and Einstein's explanation of why that has the weird properties it does, and now the Compton effect, where photons, in this case X-ray photons, are literally colliding with other particles. You must treat light as a particle. Okay? You can't get around it. There is no wave theory that can explain these three phenomena. And yet we still have that wave phenomena from the 19th century that has not gone away. So what the heck is going on? And this is really, ultimately, it gets to the heart of quantum mechanics, this dual nature. Okay, and so that's our solution. Light has a dual nature. I don't know if you've ever seen the Batman series and he had Two-Face, right? He flipped a coin, he was a good guy. If the coin came up another side, then he was evil. Okay, I'm not suggesting light has that good versus evil nature to it, but it's dual. Sometimes it acts like a wave. Other times it acts like a particle. And this is significant. It never acts both at the same time. There is no experiment that's ever been done that shows a light acting like a wave and a particle at the same time. If I choose to shoot light at double slits or multiple slits, it will always act like a wave. It will diffract and interfere. It never shows that particle nature. Polarization, explained as a wave. However, if I fire photons at targets, let's say electrons, or something that's commensurate with the with the size of the particle, it will act like a particle. It will conserve momentum like particles do. So, you know, we have a hard time trying to work that out conceptually because we're such a society where you're either this or that. We make these dualities, if you will, and light defies that. So, you know, you can put it another way. Light is what it is. It just does not follow our dichotomy that we set up very well. Okay? But we'll see the consequences of that wave-particle duality in a second. So, to finish up, all right, there is a electrons meet double slits. I'm going to show you that as a separate video. Okay, I'm not going to play it here because I don't think I'll get any audio on that. So, you know what you might actually do is pause here and watch the link that's on Schoology for this, okay? And then pick up on the notes here. Okay, so to top it all off, we jump ahead a few years. A young physicist, post-grad, named Charles DeBroglie out of France, asked a very simple question. And I'm paraphrasing. If the classic example of a wave, in other words light, can act like a particle, then can the classic example of a particle, at the time that would be an electron, can it act like a wave? Right? Very simple question. If, you know, why should we bias things towards light? Can what we consider the quintessence of a particle, an electron, that has a specific mass, specific charge, a specific location, etc., actually be wavelength? And it turns out the answer is yes. And this now blows the door open in the quantum revolution. And he went so far to propose a simple equation. He's basically saying, okay, I'm going to borrow what we found from the Compton effect. If wavelength for a photon is related to momentum as h over p, and then if we have a classic particle, momentum would be mv. Okay, so we're not introducing any new equation here, but he's just applying it to a particle. So we said, all right, well, let's see what an electron would have. So let's say an electron is moving at a tenth the speed of light. What wavelength would be associated with it? So if I apply that equation, lambda is h over mv. We put in the numbers. I'll let you substitute those in. I'll do it. 6.63 times 10 to the negative 34. Remind me to talk to you about another way we can look at Planck's constant, because there's a number of values in reference tables depending on the situation. Look up the mass of an electron, and then the velocity is given as 1 times 10 to the negative, or 7, positive 7. Punch in the numbers, and we get 7.3 times 10 to the negative 11th meters. So we see that it's a really, really small wavelength. This is on the order, I believe, of X-rays. But it's not infinitely small or unreasonably large. So that's just a hypothesis. Okay, doesn't make sense that particles would have wavelengths, but if they do, how do we test it? And the way to test it is through, like you test any other wave property. Pass it through a diffraction grating and see if it interferes with itself. Now, diffraction gratings that we use in class have a slit size of roughly this. That's way too big for this wavelength. So you need something 5 orders of magnitude smaller to do that. Well, you're not going to be able to manufacture anything like that. So what do? Someone came up with a brilliant idea. Okay, so you verify using crystals. So let me back up a second. So how could this be proven? Have a beam of electrons diffract through tiny openings. The problem is, can you make openings small enough for this prediction? The answer is yes, nature provides it for us. So think of a salt crystal where I have alternating atoms of sodium and chlorine. Okay, well, you can ask what's between these atoms. What's in this space here? It's nothing. So those act like little slits, and those openings are on the order of magnitude of what DeBroglie suggested. And sure enough, one of the most famous experiments, the Davidson experiment, and I'll show you a YouTube clip if I can find one, that just shows the results of that, showed that, yes, electrons indeed do diffract and interfere with themselves. And we've since verified this with bigger particles, protons, neutrons, atoms, and even large molecules. So our whole concept of the fundamental world has been flipped on its head. The things that make up matter, particles, electrons, protons, neutrons, are just as much a wave as they are a particle. It's just that in our everyday lives, they manifest themselves as particles, and that's what when we first discovered them, thought that's what they were. So it turns out that all of nature has this wave-particle duality. It just doesn't really show up until you get down to the quantum sizes, and it depends on which experiments you decide to perform. An electron will always behave like a particle if you do something like we did in class earlier with the magnetic field and beams, etc. All of electronics doesn't go away, but now because of this wave nature, we can do more with it, right? Perhaps the quintessence of that, or what am I trying to say? The best example of that is the electron microscope. We've talked about how you can use electrons and their associated wavelengths to form images that give you much better resolution because these electrons have such a tiny wavelength. You can't take pictures of the X-rays, at least not the classic way with the microscope, because they'll just ionize everything they hit. Okay, so I have 2 other videos here. I will link those also on Schoology, and so give you maybe a fuller flavor of how weird this all is and why looking at the nature of light sparked such a revolution. By the late 1920s, we now have this paradigm where the fundamental constituents have this dual nature. And out of this then comes our next topic, which will be the Heisenberg uncertainty principle.